Alright, so in this video we're going to take a look at the direct converter, which is building on the canonical switching cell, which we looked at in a previous video. Now if you haven't seen that video already, I'll link that in the description below so you can have a look at that and understand what it is that we're talking about when we're referring to this canonical switching cell. Now, drawn here is what we refer to as the direct converter. Now the reason this is called the direct converter is because there is always a path between, well, a direct DC path between the input and the output when the switch SXY, and this is SXY, we can say right there, is conducting. And so they call it a direct converter because there's always a direct connection. It seems logical enough. So this is one of two really main ways that we can connect the switching cell. And I mean, if you're confused as to why this looks slightly different than what we saw last time, notice that these points here, so you have A here, you have B here, and you have C here. Whereas last time we saw A on the left side, but we saw B here. So we've basically rotated that cell, and we have come to this sort of setup that we have here. So to actually do our analysis here and to actually do things that are somewhat useful to us, we're going to assume that L and C are large. And what does large mean? Large means large enough to remove any switching ripples as they're supposed to. And then what we can also do is we can assume then that the voltages and the currents are all DC quantities, so we'll use uppercase variables for those. But the first thing we're going to look at is, imagine for a second if SXY is on for a very long time. So I'm going to imagine that this is closed for a very long time. And remember, the condition is it has to be either connected between XY or XZ. You obviously can't have anything else. And it has to be one or the other. We have the condition that both switches can't be on at the same time. So we replace the two switches with a single switch like this to conceptually show what it is that we have. So imagine if SX is on for a long time. So let's say if SX is on for a long time, what you'll see is that V1 will equal V2. Maybe we can make a note. So SXY on for long time. What does that do? That creates this sort of situation that we see here. And you'll see that V1 equals V2. And you'll see that and I1 equals minus I2. Notice the direction of the current I2 is going towards the left and the direction I1 is going towards the right. So I1 equals I2. And from this, you can sort of deduce that there is, if there was a gain or some type of input-output relationship, we can say that V2 over V1 is equal to 1, and that minus I1 over I2 is equal to 1. Okay, so we'll look at later on and we'll define what these parameters are that we're looking at here, but you can kind of imagine this to be some type of gain that the converter has. So we see that if the SXY is on for a long time, the output and the input voltages become the same, and the currents are basically the opposites of one another. So I mean, fairly simple stuff. But the next thing we want to do now is we want to look at, so what happens if SXZ, so if SXZ is on for a long time, what does this do for us? So in a case like this, we see that I1 is going to equal 0, and we see that V2 is going to equal 0. Okay, and if that's the case, then we see that V2 over V1 must be 0, and I1 over I2, or minus I1 over I2, just to be consistent with what we had last time, is also equal to 0. So what we've seen here are two extreme cases of this converter. Now, I mean, what I mean by extreme cases, I mean, we can imagine that. I mean, I didn't really redraw it here. I kind of just imagined that we would be able to interpret that. But if this is the case, this is the second case we're looking at. So you see that I1 is equal to 0. I1 really can't go anywhere for a very long time. It would charge this capacitor. If after the capacitor is charged, the capacitor would act as an open circuit, and then you would have, I1 would have nowhere to go. But what we see here are two extreme cases. So you can only have either SXY can be on or SXZ can be on, right? So it can't go anything other than that. Or it can be something in between. But what we've seen here are the two extreme cases. When one of them is on for a really long time and the other one's off for a really long time, these are the two extreme cases. So when SXY is on for a really long time, we see that this sort of gain that we called it here is equal to 1. Now when we say SXZ is on for a really long time, then we see that it's equal to 0. Meaning we expect that this thing will be somewhere between 0 and 1. As long as we can control the switching state of the converter, we can ensure that the gain will be somewhere between 0 and 1. 1 being it's always on, 0 meaning it's always off. So we have to be somewhere in the middle. So if we switch this at a high frequency, then we can say the ratios will be somewhere between 0 and 1. And you'll notice that the sign of the external voltages, so V1 and V2 have the same sign as indicated by this gain ratio that we have here. And we see that the power balance, meaning the input power and the output power, which is a sort of consequence of the conservation of energy, dictates that the current ratio should be negative and the inverse of the voltage ratio. What that means is I've drawn I2 going inwards, but in reality we expect that I2 will actually go the other way. The reason we're drawing them going inwards is we're assuming that the direction of power flow right now is general. We haven't assumed any type of external network. We haven't assumed anything about anything else. We're just assuming that we have this network and we have both. This is the sort of definitions we've done. Kind of like when we saw the transformer, we always define currents going in towards the transformer, and if it's going the opposite direction, we just give it a negative sign. So I mentioned that we call this the voltage conversion ratio and the current conversion ratio. So this thing here is the voltage conversion ratio, and this is the current conversion ratio. And again, what it does is it gives you a relationship between the input and the output, and it tells you basically what type of gain you can expect from your converter. So in order to actually develop this in a sort of closed form expression, because here we've just looked at two specific cases, what we're going to do is let's look at the voltage across the inductor. Okay, so I'm going to draw some waveforms here. We can look at something a little more concrete, and really all I'm going to draw is the waveform for the inductor current. Okay, and I'm going to imagine that let's say this and something like this. So we'll say that this is dt, and we'll say that this is t. Okay, and so from 0 to dt, we're going to express. Before we go into that, we should say that we generally express this conversion ratio in terms of the series switch for the direct converter. So the series switch is xy. So the fraction of the period that SXY is on for is what we're going to call the duty ratio. So this D that we've defined in the past will be telling us for what fraction of the switching period SXY conducts. Okay? Now if SXY is conducting, then we know that VL, the voltage drop across this inductor here, is going to equal V1 minus V2, right? And on the other hand, if SXZ is conducting, then we know that the voltage drop across L is going to equal minus V2. So if we look at this waveform here, we'll see that if I call this thing VL, we have a positive voltage here, V1. Well, we don't have a positive. I'm assuming it's positive. Again, you have to start assuming something if you're drawing these waveforms, otherwise you'll be stuck forever. So I'm assuming that this is something like what we're kind of looking at. And again, this is a visual representation, but in a second I'll also physically reason with you as to why this is the case. So this we see here, we say is minus V2. Okay, so we see that VL is this for this part, and then it's this for this part. So there's a physical law known as the volt-second balance. And the volt-second balance, and I'll abbreviate that as VSB, and it essentially tells you that the average of an inductor's voltage over a fundamental switching period is equal to 0. Meaning you can't have an average voltage. And I mentioned this when we were discussing the canonical switching cell. I mentioned that you can't have an average voltage develop on an inductor. It can't sustain an average voltage. So the average voltage over a switching period should be equal to 0. So if we look at the average, then the average here has to be this area and this area. It has to be the sum of the two, which is another reason why I was saying that you have to assume one is positive and negative. If I assume both are positive, then I'm violating this volt-second balance. And so if we look at what this average is, I say VL, average. So the average for this first region, the one that's above the horizontal axis here, is going to be, well, we can integrate it or we can just look at it directly. I mean, this is simple enough to look at directly. So I can say that this has a height of V1 minus V2, and it has a width of dt. And we see that this second region here has a height of, let's say, minus V2, and it has a width of 1 minus d times t. Okay, and so this has to equal 0. And of course, this time parameter cancels out because these are averages, so you shouldn't have time in there anyways once you're done with everything. And if you simplify this, you'll find that V2 over V1 is equal to d. Okay, and again, we call this thing the voltage conversion ratio. Okay, and so it basically tells you how the voltage is converted from one terminal or one port to the other. And depending on the direction of power flow, you'll have a couple of different things happening here. So that's the voltage conversion ratio. And by the conservation of energy, remember, conservation of energy says the power that's going in has to be equal to the power that's going out in the context of this power converters. In general, the conservation of energy tells us that energy cannot be created or destroyed. But here, the power that's entering from the left side, let's say, we're going to define that as V1 times I1. And the power that's leaving the right side, supposing it's leaving, would have to be V2 times minus I2, right? And this implies that V2 over V1 is equal to minus I1 over I2, which is the current conversion ratio, and this is equal to D. Okay, and well, that's not the current conversion ratio. The current conversion ratio we define as I2 over I1. So that was a mistake on my part, sorry. 1 over D. So this is minus 1 over D. So the proportion by which you increase or decrease the voltage ratio is the inverse of how you increase or decrease the current. So this is the current conversion ratio. And these are important because now what we can do we can understand what the input and the output parameters, voltages and currents, is how they're related to one another. And I should mention that, look, we still haven't defined a direction of power. V1 and I1, and this is important to understand, this product is not necessarily positive, and this product is not necessarily negative. What the positive and the negatives imply here is that they're opposites of one another. And that's the same thing I was trying to illustrate or demonstrate here, is that this is not necessarily a positive voltage and this is not necessarily a negative voltage. But they do have to be opposite polarities relative to one another. And the reason we approach things this way is that when we get into the overall big picture and we look at it from this sort of perspective, we really understand what's going on at a fundamental level, as opposed to just memorizing some equations for a bunch of different converter topologies, right? So we have here this direct converter and the conversion ratio or conversion ratios, I should say, because we have a current and a voltage one. So this is for the voltage conversion ratio, and this is the current conversion ratio. So this is how the input and the output current and voltage are related to one another. So the direct converter itself is usually referred to as a step down or a step up converter. Now the reason for that is because if you can control the direction of power flow and you can set one voltage to be higher than the other, then you can control the relationship between the two by using D, right? So for instance, if D, let's say, is 0.5 and V2 is 5, then V1 will be 0.5 or 5 over 0.5, and V1 you can calculate based on that. So you can always control which way the power is flowing, and you can always control how much you increase or decrease the voltage by. So we say that you can call these, I guess, well, in general they call them, you can either have a step up. So step up sometimes is called a boost, and that means that the power goes to, let's say, higher voltage, right? And then you have a step down, which we call a buck converter, more commonly. And this one, P, goes to lower voltage. So the direction of power flow is what distinguishes the two. Other than that, they're basically the same thing, physically speaking at least. And so what we'll do now is we can look at how to implement this converter using switches, because this type of switch that we've seen here is not really a practical thing. This is more of a conceptual idea. So now what we can do is we can sort of decompose this switch into two switches, and then we can look at how the two different switches behave, and then based on that we can start to understand how we can actually create a practical converter based on all of this stuff. So we have a switch that looks something like this, right? So our switch is like this, and we can imagine that this is Z, this is X, and this is Y. And so you can basically decompose this into two different switches. You can say that it is one switch that does something like this, plus another switch that, let's say, does something like this, right? And what I'm going to do is I'm going to call this YX. I'm going to call this XZ. Okay, and this current here is obviously IY because it goes through that switch. This is the series switch, and this one here we call the shunt switch. And here, this one I'm going to call IX prime. And the reason I'm going to call this IX prime is because this current is not technically the same as this current here, but this current IY really is, because here we're decomposing it into two, so I don't want to confuse the two and take the same name. So we'll call this IX prime. And so the way we're going to switch this this pair of switches is as follows. So we're gonna, if we look at V, or if we just look at the voltages, I mean, we can ignore how we're going to switch things and all that kind of stuff. Well, I guess in essence, that's what we're looking at when we do those things. But if we imagine here that this is dt and that this here is t, then what we'll see is if we call this Vyx and we call this Iy, then you'll have, this will be 0 for this time because this is the series switch, remember, and an on switch has a 0 voltage drop, ideally at least. And so this is on, and while this is on, this will be conducting some current, obviously, otherwise it's not really on, is it? And the magnitude of this current that it will conduct, we're going to call minus I2, and this voltage here will be V1. So that's the voltage drop across Vxy when this thing is on. Now on the other hand, this XZ switch that we have will do something like this. So we will again, this is dt, and again remember we define dt, or we define d at least, as the fraction of the period for which the series switch conducts. And so if that switch is conducting from 0 to dt, then this switch has to be off. And an off switch, remember, has a voltage across it. And an on switch, so this is on between dt and t, will do something like that. And on the other hand, maybe we can move this way for a second because we'll have to go downwards. On the other hand, what we're doing is, well, I guess technically I should have drawn that downwards, but it doesn't really matter. Or maybe we can do that now, because this is negative. I don't want to confuse. I guess logically speaking, we talk about things this way, but overall it makes really no difference, because again, we haven't defined any positive or negative directions here yet, right? So this is minus I2, and so yeah, we want to do the same thing on this side here. And so this will be, but this happens in the other part, right? So this happens during this time here, like this. And so this here will be dt, and this is one full switching period. This is the same current minus I2, and this is the voltage V1. And so we can probably label this Ix prime, and we can label this Vxz. right? So that's what these voltages, or that's what this switch is being subject to for the two different, I guess, intervals of switching. So if we consider the direct converter, because again, this is still general, this is a decomposition of the switches. So if we consider the direct converter operating as a buck converter, that means power, well, if we consider this circuit, power is going to flow from a higher voltage to a lower voltage. That's the definition of a step-down converter. It steps the voltage down. So V1 is going to be higher than V2. That means, let's say V1 is greater than V2. So we're going to say that V1 is greater than 0, V2 is greater than 0, I1 is greater than 0, this current here, I1, so the current is going to go towards the right. And this current I2, because it's defined going towards the left, but we said the power is going to flow towards V2, that means this current is actually going to be negative. So I2 is going to be less than 0. But all that really means is that the current is going towards the right in this case. Because again, power is flowing from high voltage to low voltage. That's the definition of a buck converter, or step-down converter, right? So in a step-down converter, V1 is greater than 0, V2 is greater than 0, I1 is greater than 0. So maybe we can write that. So V1 greater than 0, V2 greater than 0, I1 greater than 0, and then I2 less than 0, because it's going towards the right. Now, this, in this case, we have this type of situation. The current of the series switch, so the current IY that's going to go through SXY is going to be positive, right? Right. And the voltage that drops across this switch will also be positive because V1 is greater than V2. So V1 minus V2 will also be, well, it's V1, it's starting V1 minus 2, it's just V1. That'll be greater than 0. So if you have a positive current and a positive voltage, what that means is you can use a transistor for this switch, right? Because in a transistor, you have a positive voltage and a positive current. And again, we looked over that in the introduction type of concepts of how power semiconductor switches work. But the transistor is positive current, positive voltage. Now, on the other hand, in the shunt element, so this XZ switch, you have the current and the voltage are going to be opposite. So the voltage you'll see is defined this way, but the current is going to go up this way. And if you remember in the video where we conceptualized the converter, we saw that the current was a minus current that was going up, remember, because we had a smaller current here and we had a larger current here. So we required current to come up from this shunt branch. And so the only way you can have current and voltage in the opposite direction in any type of switch is if you have a diode. Well, in the simplest case. So what we're going to do is we're going to create then the buck converter, or a practical version of the buck converter. Okay, so we're going to say that the input is a capacitor, and because you always need your filters no matter what. And so you have this filter, and again, this XY switch, we're going to say it's a transistor, so we're going to draw it as a MOSFET, because that's the most commonly used transistor these days. And this shunt element is the diode. Okay, and again, this is the practical sort of, if you were to put a circuit on a breadboard that were to act as a buck converter, it would have to look like this. You can't use these ideal switches; they don't exist, right? So we're going to say this is Y, this is X, and this is Z, right? I'm going to call this L, and we can call this C, and obviously this is V1, and this is V2. And again, what I'm going to do is I'm going to label this as I2. I'm going to label this as I2, and I'm going to label this as I1. And I guess we can also label this here as VXZ if we want. And then you can also label this current here as IL. We can call this Q if we want. I don't want to call this diode D because we use D for the duty ratio, but you can label the diode if you'd like. But the thing to take away here is that the power is going this way. Okay? Okay. So, what have we done? We've taken this general conceptual idea of a direct converter, and we've implemented it based on the requirements of the switches, which we saw here. We've implemented it as a practical circuit. So this is the buck converter circuit. And this, if you look at any circuit schematics online, if you look at most textbooks, this is what the buck converter or step-down converter will look like. They'll draw the actual thing like this, and if you implement it, it'll have to be like this. So this is the buck converter. So what we're going to do is we're going to stop here, and we will look at the boost converter in a separate video. Otherwise, this video will probably get way too long. And we will, in the next video, we'll use the same principles, but we will develop what the boost converter should look like, again, based on the exact same direct converter topology, because again, we can, based on the connection of the switches, we can establish a different topology basically, and it can serve a different function for us. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.